Hello, welcome to another module in this massive open online course. So, we are looking at the Z transform. Let us continue our discussion on the Z transform, look at another technique to compute the inverse transform. This is known as the general inversion method. Okay. So, this is the inverse Z transform. So, what we want to look at? We want to look at a technique to compute the Z transform through the what is known as the general inversion technique. The general inversion method to compute the inverse Z transform is as follows. What we would like to do is basically, let us say x z is the Z transform, given Z transform, then x n can be computed as the integral, or let me write it 1 over 2 pi j. This is a contour integral x z z to the raised to n minus 1 dz, and this integral that you are seeing over here, this is what is known as a contour integral, evaluated over a contour, okay, in the z plane. Okay. And what is this? And this is evaluated over this contour gamma, and this gamma is basically a closed contour in counterclockwise sense, in the counter clockwise sense, enclosing all the poles, and this is important. Enclosing all the poles, correct? Enclosing all poles. So, this gamma, so this integral has to be evaluated over this contour, closed contour gamma, which is a closed contour in the counterclockwise, or basically the anti-clockwise sense. It encloses all the poles of x z into z raised to n minus 1, and has to be in the region of convergence of this Z transform, and this has to be inside the ROC, inside the region of convergence. Okay. So, this is basically you can show that x n equals 1 over 2 pi j, the integral, the contour integral over this contour gamma of x z times z n minus 1 dz, where gamma is a closed contour. So, closed contour in the anti-clockwise sense encloses all the poles of x z z n minus 1, and the contour is inside the ROC. Okay. So, the contour lies inside the, so gamma lies inside the ROC. Let us make that contour lies inside the ROC, and it can be shown that this can be simplified as follows. This is 1 over 2 pi j contour integral over gamma x z z raised to n minus 1, which is equal to summation I equals 1 to p summation over the residues z residues evaluated at each pole pi of the quantity xz raised to z raised to xz into z raised to n minus 1. So, this denotes the residue, what is known as the residue. I will define this shortly. This is the residue at pole pi, and this quantity p equals the number of poles of xz into z raised to n minus 1, and therefore, what this is basically the sum of all the residues evaluated at the poles, okay, sum of all the residues at poles, summation over all residues at poles. Summation over all the residues at the poles of xz z raised to n minus 1. Now, what is the residue? Now, if pi is a simple pole, that is basically multiplicity equals implies that is it is a pole of multiplicity 1, that is you only have a factor of z minus pi, okay, implies the multiplicity equals 1. The residue equals of this simple pole is limit z tends to pi z minus pi xz of z raised to n minus 1, or in most cases can be simply evaluated as z minus pi into xz into z raised to n minus 1, that is evaluated at z equal to pi. Okay. So, this is the residue at a simple pole pi, that is a pole of multiplicity 1. This is simply given as x minus zi, or no, sorry, z minus pi into xz into z raised to n minus 1 evaluated at z equal to pi. Now, for a pole with multiplicity r, where r is greater than or equal to 1, now for any general multiplicity, for pole with multiplicity, let pi equals pole with multiplicity r, then the residue of this equals this is 1 over r minus 1 factorial with multiplicity r greater than or equal to 1, 1 over r minus 1 factorial z limit z tends to pi d raised to r minus 1 over dz raised to r minus 1 z minus pi raised to r xz into z raised to n minus 1. This is the residue of a pole with multiplicity r greater than or equal to 1, that is with any general multiplicity. With multiplicity r greater than or equal to 1. All right. So, evaluate the residues, all right, of the transform of xz into z raised to n minus 1 at the different poles, and then we sum all the residues at these poles. That gives us the value of xn. All right. So, to understand this better, let us do a simple example. Let us do a few examples. All right. So, using this general inversion technique, for instance, let us do this simple example. Let us evaluate the inverse Z transform of x equals 1 over twice z minus 1 into z plus half. Now, for n greater than 0, we have x into z raised to n minus 1 equals z raised to n minus 1 divided by twice z minus 1 into z plus half. Now, the poles are at z equal to 1, z equal to minus half. Z equal to 1 comma minus half. Therefore, x n is the sum of the residues evaluated at these poles. That is, basically you will have, well, the residue evaluated at z equal to 1 of we have two poles, correct. So, we have the sum of the residue evaluated at z equal to 1 of x z into z raised to n minus 1 plus the residue evaluated at z equal to minus half of x z into z raised to n minus 1. Now, the pole evaluated at now residue at z equal to 1 at z raised to n minus 1 equals basically, well, z minus 1 into x z into z raised to n minus 1 evaluated at z equal to 1. This is equal to, well, z raised to n minus 1 over twice z plus half evaluated at z equal to 1, and this is equal to, well, z raised to n minus 1 raised to n minus 1, that is simply 1 divided by 2 into 1 plus half, that is 3 over 2, which is equal to basically 1 over 3. Okay. So, that is basically your residue at z equal to 1. Now, let us look at the residue at z. Now, the residue at z equals, now that evaluates the residue at z equal to, now the residue at z equals minus half of x z into z raised to n minus 1. The residue at z equal to minus half, that is basically z minus pi or z plus half into x z into z raised to n minus 1 evaluated at z equal to minus half. Okay. So, that is the residue at z equal to minus half, z equal to minus half, that is basically your that will be z raised to n minus 1 over twice z minus 1 evaluated at z equal to minus half. So, this will be your z raised to n minus 1 minus half n minus 1 over twice z minus 1 minus half minus 1, that is minus 3 over 2. So, this is basically minus 1 by 3 into minus half raised to n minus 1, and this is the residue at z equal to minus half. Therefore, x n is simply the sum of these two residues, that is residue is equal to 1 z equal to 1 plus residue at z equal to minus half, that is 1 over 3 minus 1 over 3 minus half raised to n minus 1. Remember, this is for n greater than 0. Now, for n equal to 0, for n equal to 0, what we obtain is the following. So, consider x z into z raised to n minus 1, n equal to 0. So, n minus 1 equals minus 1. So, this is simply x z over z. Now, x z into 1 by z or x z over z equals 1 over twice z into z minus 1 into z. Now, note that because of this at n equal to 0, because of this division by z or x z by z, we have this additional pole at z equal to z equal to 0, all right. So, because of this z raised to n minus 1 n equal to 0, so that will be z raised to minus 1. So, because of that factor, we have an additional pole at z equal to 0, which we have to take into consideration while evaluating the sum of the residues. Okay. Now, therefore, we have poles at z equal to 0, comma 1, comma minus half. Now, x 0 equals z into x z over z evaluated at, that is x z into n minus 1, which is x z over z evaluated at z equal to 0, which is basically your 1 over, no, this is not x z, this is residue at 0. One over, this is basically your 1 over twice z minus 1 into z plus half evaluated at z equal to 0. So, this is 1 over twice minus 1 into half equals minus 1. So, this is basically your minus 1. Now, residue at z equal to 1, this will be z minus 1 into x z over z evaluated at z equal to 1. So, this will be basically 1 over twice z into z plus half evaluated at z equal to 1. So, this is 1 over twice z is 1. So, twice z plus half 3 by 2, that is 1 over 3. This is your residue at z equal to 1. And the residue, finally residue at z equal to minus half is z plus half into x z over z evaluated at z equal to minus half. So, this will be 1 over twice z into z minus 1 evaluated at z equal to minus half. So, this will be 1 over twice into minus half into z minus 1 equals minus 3 over 2. So, this will be plus 2 over 3 actually. So, x of 0 is basically the sum of residues. So, now you get for n equal to 0, x of 0 equals sum of residues at z equal to 0 x of 0 is the sum of residues at the poles. Remember, there is an additional pole at z equal to 0. So, the sum of the residues at z equal to 0, z equal to 1 and z equal to minus half, which is basically minus 1 plus 1 by 3 plus 2 by 3, this is 0. So, x of 0 equals 0. Okay. So, x of 0 equals 0, and therefore, what we obtain is basically x of n equals 1 by 3 minus 1 by 3 into minus half to the power of n minus 1 for n greater than or equal to 1, which can be written as 1 by 3 minus 1 by 3 into minus half to the power of n minus 1 into u n minus 1. Alright. So, this is basically your inverse Z transform, okay, evaluating using the general inversion technique. Okay, this is your inverse Z transform. Okay. Let us now look at another simple example again. Example number 2. Find the inverse Z transform of x of z equals z square over z minus 1 square z minus e raised to minus a t. Okay. Now, consider x of z into z raised to n minus 1 or z raised to k minus 1 to evaluate x k. This is equal to, well, z square into z raised to k minus 1. So, z raised to k plus 1 divided by z minus 1 square into z minus e raised to minus a t. Now, note that this has a pole of there is a simple pole at z equal to e raised to minus a t. And there is a pole of multiplicity 2 at z equal to 1. All right. So, there are two poles. At z equal to 1, you have a pole of multiplicity 2 because you have a factor z minus 1 square, and at e raised to minus a t, you have a pole of multiplicity 1. Okay. Now, first let us find the simple residue. Residue at z raised to z equal to e raised to minus a t, that is basically simply z minus e raised to minus a t into x z into z raised to k minus 1, that is basically your z raised to k plus 1 divided by z minus 1 square evaluated at z equal to e raised to minus a t, that is e raised to minus a k plus 1 t over e minus a t e raised to minus a t minus 1 whole square, which is also your e raised to minus a k plus 1 t over 1 minus e raised to minus a t whole square, and this is basically your residue at z equal to e raised to minus a t. Now, we still have to find the residue at z equal to 1. Remember, at z equal to 1, we have a pole of multiplicity 2. So, we have to use the general formula for the formula for computing the residue for a pole at a pole with multiplicity r greater than or equal to 1. All right. So, here you have pole of multiplicity equal to 2, okay. That is basically the formula, you have to set r equal to 2, okay, and that gives you, what does that give us? Well, residue is 1 over r minus 1 factorial d over d to the r minus 1, that is d over dz of z minus 1 whole square x z into z raised to k minus 1 equals, well, d over dz, and this is evaluated at z equal to 1, and this is d over dz, which reduces to d over dz of z minus e minus a t evaluated at z equal to 1, and this derivative is basically can be computed as follows, that is k plus 1 into z raised to k by z minus e minus a t minus z raised to k plus 1 over z minus e raised to minus a t whole square evaluated at z equal to 1, substitute z equal to 1. So, that gives us k plus 1 over that gives us k plus 1 over 1 minus e raised to minus a t minus 1 over 1 minus e raised to minus a t whole square, which you can further simplify as 1 over k over 1 minus e raised to minus a t minus e raised to minus a t by 1 minus e raised to minus a t whole square. Okay. So, this is basically the residue at z equal to 1. And therefore, finally, x n will be the sum of these two residues, that is e raised to minus the residue at e raised to z equal to e raised to minus a t, e raised to minus a into k plus 1 t over 1 minus e raised to minus a t whole square plus k over 1 minus e raised to minus a t minus e raised to minus a t divided by 1 minus e raised to minus a t whole square, which is now k over 1 minus e raised to minus a t, and you can simplify bringing the first and last terms together as e raised to minus a t into 1 minus e raised to minus a k t divided by 1 minus e raised to minus a t whole square. This is your x k for k greater than or equal to 0, that is for, and this is valid for k greater than or equal to. Okay. So, basically that completes the problem. All right. So, what we have seen here is basically we have seen a different technique to evaluate the inverse Z transform, that is basically using the general inverse technique, and we have seen a couple of, that is using what is also known as the method of residues, that is evaluating x n as the sum of the residues of the poles, sum of the residues at the poles of x z into z raised to n minus 1, and we have seen a couple of examples to understand this technique better. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.